opportunity to present this. Sorry, not used to that. Sorry. Okay, won't do that again. So this is a joint work between myself and Jan about FreeSpec. FreeSpec is, in a nutshell, a general-purpose framework where we want to try to implement and certify Impure computation in Coq. We implement Impure computation using a free monad, as it's usual in Coq, indexed by so-called interfaces. You can see an interface as a set of impure primitives that you will be used to do your computation. And we certify this impure computation using contracts. So this is not the first time we had the opportunity to speak about FreeSpec during an academic conference. The first time was during Formal Method 2018. And we presented the foundation of the formalism. Basically, the idea is that you can break down a complex system into interconnected components implemented or modeled as impure computation and cooperating through interfaces. And the first version of the formalism was really about how you can compose everything together, the interfaces to do the components themselves, and the contracts to do some correctness proof about a system. In the second version of FreeSpec, on the contrary, we really want to make easy to use the formalism to do the actual proof. So we have made several updates in the formalism and implemented several quality life improvements like proof engineering stuff for the framework to be more easy to use and the proofs that you write more easy to reuse in different contexts. This is part of a more long-term goal, which is the idea that you can use Coq as a general functional programming language, like you can do with Haskell or something like that. And to achieve this goal, we have a different kind of interconnected project. We have a prelude function, a prelude library with the usual type class hierarchies, but also some new convenient strings. We start to use the new integers, primitive integers of Coq in this library, so you can use it in your development. We have also implemented a parser combinators library to do parsing easily in Coq. And of course, we have FreeSpec. And now we are in a state of thing where we can try to do demonstrators. We had a PhD students that tried to re-implement R in Coq and to actually be able to pack and unpack R archives and show that there is some proof with respect to how the file system behaves when you try to read and write the file from files. And with Jan for this paper, we implement mini HTTP server, which is analogous to the simple HTTP server of Python. I don't know if you're familiar with it, but basically it's a simple read-only server, so you can use to serve static files over the internet, mostly for debugging purpose. And we do basically that in Coq mini HTTP server. And we also make some proof of correctness about the implementation. More specifically, that we try to correctly use a file system. We don't try to read from a closed file descriptor, for instance, or we close all of our file descriptor. It's simple in mind, and we wanted that it's simple to actually write the proof, because it's complicated. FreeSpec is not usable. So in the 15 minutes or so that I still have left to talk to you, I will try to explain how we have implemented and certified mini HTTP server, and hopefully we will have time for some questions. And I will try to do some things that I'm not really used to, and that show you some code, because the goal is to show you that it's easy to read and easy to understand. So the first step of writing mini HTTP server was to actually implement it. And to do that, we wanted that FreeSpec allows for writing idiomatic monadic code. So this is the part where, sorry, I need to do some first. No, sorry. Sorry. Okay. I didn't want that to go that way, but it's okay. I will do. Too many things. Okay, this is better. So this is the code of the implementation. I will try to increase that, and I will show you one, I think, good example of an impure computation. It's basically how you read from a file, the content of a file. So the main idea is that you could have written this in OCaml. We try to reuse the newly introduced let operators of OCaml. You have the semilecon to express the sequentiality of impure computation, so the implementation is I would say boring from a functional program point of view. For the types, there are more things that can be read. So it's an impure computation. Impure is actually a type that takes two arguments. The first one is the interface that the computation is actually using. The second one is the return time. It's pretty conventional. We didn't invent anything there. This computation is actually using two different interfaces, and this is shown here with the provide two type class constraints. So we explicitly say that this impure computation with content shall be used in a context where at least we can provide file system and console, which are two interfaces. So I can just jump to the file system definition, which is interesting.
It's not so the extensible interfaces sort of thing. So it's like we can't do some sort of interfaces. So we can't have like a single type class that accepts like the data type colocated style of like several interfaces combined into one, right? So you have to have explicit amount of interfaces encoded in this.
Well,
provide one, provide two, provide three, and so on, right?
Oh yeah. Well, it's mostly for the thing to remain usable. I try to implement some kind of generic type class that allows to aggregate a lot of one. But after that, the type class mechanism, resolution mechanism gets a bit mixed up. So I found for now it's easier to have this effectively provide one, provide two, and so on. And hopefully I will try to fix that in the future. So basically, you can easily define interfaces as inductive types, parameterized by the return type. So for instance, for the file system, you have the open primitive that takes one argument, which is basically a string, and returns return one thing, which is a file descriptor. And you can have, for example, it's a read-only interfaces, so you have file exist, read and close, and that's all. And once you have this interfaces, you can define impure computation using an helper which is called request, which is basically ask for the primitive to be resolved, and wait for the result, return the result. And then you can combine these small function with the monadic let operator. So once you have done that, you can start to implement other stuff. For instance, you have a generic TCP server which take an impure computation to compute the actual results. We create a server, we listen incoming response for a certain amount of time because we are in COC, and for now the non-terminal recursion is not our priority, but it will be soon. I will come back to that. But for now, we just do, for a certain amount of time, we wait for our client, read the socket, give the message to the handler, write the response, and so on. So this is enough to implement in a, I would say, conventional, idiomatic way an HTTP server in COC using FreeSpec. Of course, if you just want to use COC to write code, it's a bit a shame. Coq comes with a lot of good opportunities to actually reason about the correctness of your code, but it comes with things about pure computation. So FreeSpec tried to fill the gap by providing contract types, which allows to reason about the correctness of an impure computation that use a given interface. There are three main components. The first one is a witness, which is basically a value that evolves among time and tells what happened before, so you can decide which primitive you can use at a given time and what to expect from the result. So you have this, it's basically an abstract type for the implementer. You can update it after each primitive that you have executed, and you have a result, you get a new witness, and now you can easily instrument the execution of, during the proof, you can easily instrument the implementation of your impure computation for this witness to be up to date. And then you define two things, the color obligation and the collie obligation. The color obligation is about limiting the range of primitives you can use at a given time. So for a given abstract witness, it gives you a set of primitives that you can use. And the collie obligation is about reducing the amount of response you can get from a primitive. So from a given witness and a given primitive, you get a set of results you can have. And in FreeSpec user, by defining contracts, they specify how an interface shall be used and what to expect from an interface. So I will quickly show you how you can use this contract system to specify a contract for how to use correctly the file system. As I said, the first thing is to consider, the first thing is to consider the witness. And basically, we only reason about file descriptor and which are correct and which are not correct to use. So our witness state will just be a set of file descriptors that we implement as a function, which return true when the element, the file descriptor, is in the set and false when it's not. I've provided several functions to manipulate these states, which are not really relevant for now, but it's more, it's pretty usual for that. And then we can define the update function. So to define the update function, we need to consider how set of file descriptor will evolve over time. So basically, when we open a file and we get a file descriptor as a result, we want that the new witness contains this file descriptor. On the other hand, when we close the file descriptor, we want to remove this file descriptor from the set of open file descriptor. And finally, for read and file exists, we do nothing in particular, and we just return the same file descriptor set. So now we can instrument the execution of impure computation to have the set of file descriptor open, and we can start to provide obligation both for the caller, so the impure computation itself, and the collie, which is the implementer of the interface. For the caller obligation and the collie obligation, I found that it's easier to define them as inductive products for the automation of Coq. Basically, we do not restrict anything particular for open and file exists. We can open any file. We can check if any file exists. However, for read and for close, we ask that their argument is member of the file descriptor set. So this is done, and now we can reason about the obligation of the collie, so the implementer. I found it maybe less obvious to explain, but basically we do not have much to ask about the implementer. We do not really care about if he returns the correct content of a file, for instance. We are not reasoning about that for our proofs. What we really want to avoid is a scenario where an impure computation will correctly use the interface, but basically end up using an already closed file descriptor. And one thing to avoid in particular is that if open is able to return an already open file descriptor, and then you close the previous one and try to use the new one, which both are basically the same, you think you are correctly using the interface, but you are not because of this mix-up. So you can ask for the result of open to be absent from the file descriptor using this obligation. And when you put everything together, you end up defining what is a contract. So the type is actually more interesting than the definition. So it's a contract for the file system interface, and it uses the witness, the FD set witness set. Okay, so now we have specified how we want to use the interface, and can we prove that the HTTP server, the mini HTTP server, is actually using it correctly. I found myself, I think that there is two different properties that we want to reason about when we reason about the correctness of an Impure computation. The first one is, do we use the interface correctly? So it's basically about contract compliance. We always satisfy the caller obligation. The second one is to reason about the output, the outcomes of our execution, both in terms of witness state and in terms of actual results that we compute. To do that, FreeSpec provides two predicates, and the first one is basically that, the contract compliance. You prove that no matter the execution path, you always respect the obligation. And the second one is a way to given an execution, explore the possibility, the potential value of the final witness state and the result, and see if they respect some predicates. So I will try to go quickly for this one. The main idea is that the definition of these both predicates I quickly spoke about are really related to the internals of FreeSpec, and I personally don't want FreeSpec users to care about that. I don't want them to know the definition of the free monad, because it's not what they want to do. They want to write impure computation. So just to show you how we can certify the read content, for instance, because so as I said, read content is basically opening a file, reading its content, and closing the file. It should be straightforward. So I think it's better like that. So we want to prove that who read content is respectful. Sorry. So, and basically there is a tactics called prove impure, and what the tactic called is unrolling the computation, exploring as many control flows as possible with some restriction already, and generating the obligation about your contracts. It can be useful to show you, even if I don't want you to know, but to show you how it looks like when you try to do it manually. Without it, you get some internals definition, and in addition, you get the use of primitives that are not related to your interface. For instance, this read content file is doing some logging, but we don't care about that. Prove impure basically solves them for you. And basically, during this provide different obligations that you can solve the same ways that we would do for any cock proof. In practice, I have put several lemmas in a hint database, and they are enough to prove everything. The second thing that we want to prove is something called FD set preserving. It's the idea that if I execute read content, the witness state before and after is exactly the same, and therefore I have not forgotten to close any file descriptor. And once again, there is a tactic for that, which basically take an hypothesis of the form respectful run and try to explore the different possibilities linked to the implementation. So here we show that there have been a first call to open, and we know that it respects the caller obligation. We know by hypothesis that the caller obligation is also satisfied, and therefore we can have this list of hypotheses, and we need now to prove this. So let's go on. An interesting idea. Yeah, just want to say that, and after that I'm done. An interesting idea is that once you have proven this kind of properties, you can make the implementation of real content opaque, and FreeSpec will honor that and let you try to prove things without giving any information about the read content. To conclude this presentation, we also add something to FreeSpec is the capability to do some OCaml FFI and to execute actually impure computation from coq. So for instance, I have this file where I basically I'm asking for executing HTTP server 100 times. I can just do coq.c HTTP main.v. Now I have the server that is running, and it's a yellow one, and I can show you my conclusion slide if everything works. Okay, so it worked, but again, it's in 3. Yeah, my conclusion slide. So served by coq itself. FreeSpec 0.1 was about principle of composition. We tried to make FreeSpec more usable now. In future version, we want to try to explore more things like general recursion, or not being limited by the termination of coq. And finally, we hope to release soon enough 1.0 version for you to use it.
All right, thank you.
Sorry.
Let's take time for one question.
I noticed that the way you have witnesses set up, the function that computes a new witness needs to be computable. Yeah. And witnesses remind me of ghost state and a lot of verification frameworks where you can advance ghost state in non-computable ways. Are there any downsides to forcing it to be computable?
Well, it remains an open question. My initial intuition was that it would help coq to reduce as thing goes. I'm not that sure anymore. So yeah, a completely honest question would be to try to relax the fact that it's total and see if we can keep the level of and keep basically as usable as now. I think it can be. So it's just finding the time to try it, basically.
Okay, thanks.
Okay, so since the next break was anyway 10 minutes and we ate it up almost completely.
Sorry.
Let's take just 3 minutes break. One thing I still wanted to mention is that for lunch we're going on the 8th floor. So the CPP people, we are too large for this floor, so we are going to the 8th floor. But this is after the session.